Remember that bromine here, and then this is a CCl4. That's just a solvent, by the way. So if you remember that, I forgot to put the line. So this is a radical reaction. So the bromine with a radical, it could be NBS, then you make a bromine radical. Bromine radical is going to abstract the hydrogen from this carbon, and then since the one's there, probably the most likely one to form is allylic cation, right? Allylic radical. So this hydrogen there, that's allylic hydrogen, but this another allylic hydrogen, there's another allylic hydrogen. We have 3 allylic hydrogen there. So what it means is, if this bromine hit this hydrogen, you're going to have a radical there, that carbon. That's a allylic radical. If you have this bromine hit that hydrogen, that allylic hydrogen, then you get the radical growth of another allylic position. And then we got one more. If the bromine captures that hydrogen, then we're going to create a radical on the different allylic position. All 3 of them are allylic. All 3 of them are allylic. And then all 3 of them will be resonance stabilized. This one's going to be resonance stabilized, right? This can be here, that can go there. That could be resonance stabilized. So it can go, double bonds goes here, radical goes there. This one is also going to be radical stabilized. So that radical goes here, there. So we are talking about 6 different allylic radicals going for the bromination reactions, and each one will produce, and then which one's going to be major. So that is a very difficult task right now. So in order to solve that, you've got to remember what we discussed. First of all, let's talk about what products it produces. This allylic radical captures the bromine, then you got the bromine at that value position. And that one can go through the same thing. If that captures the bromine, you got the bromine comes here. But you already know that these 2, even though it was drawn differently, they are identical, right? So it doesn't matter. Either will make the same products, but not the other 2. If that one goes through the bromination, we got bromine sitting on that carbon, that's it. If that one goes through the bromination, we got bromine sitting on that carbon. Right? That's 2 different products going to be formed by the 2 different resonance structures. And this one, bromine is going to go there. This is a product. Bromine can go there. That's another product. So it's not 6 products that we're going to get. We get 5 products. We still have a more than 1. There's a potentially 5 products. 1, 2, 3, 4, 5. So out of 5, which one is the major? That is the question. See how complicated these things are? In OChem 1, since we didn't explain, you can pick any of those 5 and you tell me that, oh, you're right, you give all the credit, but not anymore. Why? Because we just learned the concept of which one is going to be major product, which one's going to be minor product, depending on how you do the reaction. Let's say that you, in order to do that, let's compare the stability of the products. We have a product, right? This one, that one, that one. Which one's the most stable product? Since there's double bond there, we are using stability double bond as an energy of the product. This one, 1, 2, 3 substituents, tri-substituent double bond, right? This one, 1, 2, 3 substituents, so tri-substituent double bonds. This one is 1, 2, that's double substituent double bonds. And that one's 1, 2, 3, tri-substituent double bonds, and that one's just 1, 2, di-substituent double bonds. So if you pay attention, most stable double bonds, then you should pick these 3, because those are tri-substituent double bonds. They are more stable ones compared to the other 2. So if you provide enough energy, let's do this reaction at 100 degrees. Then you have enough energies to go over all the highest mountain activation energies, then you will produce the most stable product. That will be the most substituted double bonds. So it's still not the one answer, but at least all these 3 are potentially the major product. But what if you lower the temperatures? You do the reaction -100 degrees. then you should go to the most stable intermediates. That means, is this the most stable intermediate? Or either of those two most stable intermediates, or even these two most stable intermediates? That is what you should consider. Allylic radical. That's a secondary allylic radical. That is a secondary allylic radical. That is a primary allylic radical, so this is probably not ready. That is a secondary allylic radical. Then the secondary allylic radical, look at that one. 1, 2, 3 substitution there. There's a tertiary allylic radical. So if you do the reaction at low temperatures, this is probably the one that goes through the most, because that's the most stable intermediate. That will produce that one as a kinetic product.